Welcome to the AI and GIS Frontier podcast. Let's get into today's topic.
Today, we are doing a deep dive into one of the most practical applications of AI and satellite imagery in forestry. Using Sentinel-2 and drone data with machine learning to monitor reforestation, track sapling density, and assess seedling survival. This is where the technology is directly replacing boots-on-the-ground surveys and saving forest companies and agencies enormous amounts of time and money.
This is a topic I find fascinating because it hits right at the core of silviculture work. Traditionally, how does reforestation monitoring work, and what are the pain points?
Traditional reforestation monitoring is incredibly labor-intensive. After a site is planted, a silviculture crew has to go out and do stalking surveys, usually walking transects through the cut block, counting seedlings and sample plots, measuring heights, assessing health, and recording species. In Canada, provincial regulations require these surveys to confirm that a site meets free-to-grow standards, meaning the planted seedlings are established and competing vegetation is not overtopping them. For a large forest company managing hundreds of thousands of hectares, this means deploying dozens of field crews every summer. The cost is substantial, the data is sparse, because you are only sampling a fraction of each block, and the results take weeks to compile. If a block fails the stalking survey, you might not know until the next growing season when it is too late to intervene efficiently.
So where does satellite imagery fit into replacing or augmenting that workflow?
Sentinel-2, which is the European Space Agency's freely available satellite constellation, captures multispectral imagery at 10-meter resolution with a 5-day revisit cycle. That gives you regular, wall-to-wall coverage of every planted block on your tenure. The key innovation is using machine learning to extract meaningful silvicultural information from that imagery. Researchers have shown that you can classify plantation age classes, distinguishing young plantations at 4 years, middle-aged at 10 years, and mature at 15 years, with high accuracy using support vector machines trained on Sentinel-2 data. A study using random forest regression in New Brunswick's Acadian forest showed you can estimate sapling density from Sentinel-2 imagery, and when you integrate LiDAR data, accuracy improves by about 15% over Sentinel-2 alone. The big picture shift is going from point-based sampling to continuous wall-to-wall monitoring.
Let us talk about the actual workflow. If a forest company wanted to implement this today, what does the process look like step by step?
There are roughly 5 stages. First, you need a baseline. You collect Sentinel-2 time series for your management area, going back several years if possible. You process this through Google Earth Engine or a similar cloud platform to generate vegetation index time series, primarily NDVI and other spectral indices. Second, you need training data. This is where your existing stalking survey data becomes incredibly valuable. You take your field survey results and geo-reference them against the satellite imagery to train a machine learning model. Third, you train the model. Random forest and support vector machines are the most common classifiers, though deep learning approaches using temporal convolutional neural networks are showing improved accuracy, especially when you leverage the full-time series rather than single dates. Fourth, you run inference across your entire management area, generating wall-to-wall maps of regeneration status, stalking density estimates, and growth trajectory classifications. Fifth, you validate with targeted field checks. Instead of surveying every block, you send crews only to blocks where the satellite-based assessment flags concerns.
That fifth step is the game changer, isn't it? Going from blanket surveys to exception-based field verification.
Exactly. It flips the entire model. Instead of asking field crews to confirm that everything is fine across hundreds of blocks, you are asking them to investigate the 10 or 20 blocks where the AI says something might be wrong. One study estimated that this approach can reduce field survey costs by 60 to 70%, while actually improving overall monitoring coverage because you are getting data on every single block, not just sampled ones. A forest district that used to budget 6 weeks of field crew time for stalking surveys might cut that to 2 weeks of targeted verification.
Now, Sentinel-2 at 10 meters is great for landscape-scale monitoring, but you cannot see individual seedlings at that resolution. That is where drones come in, right?
Right. And this is where the technology gets really exciting. Drones capture imagery at sub-centimeter resolution, 0.3 centimeters per pixel in some systems, which means you can see individual seedlings clearly. Researchers have been training convolutional neural networks, specifically faster RCNN architectures, to automatically detect and count seedlings in drone imagery. The accuracy results are remarkable. a study on white pine seedlings in New York achieved 91% overall accuracy in medium-density blocks and 90% in high-density blocks. Finnish researchers detected planted spruce seedlings with 97.86% detection accuracy. A study in New Zealand on Pinus radiata achieved 99.5% sensitivity, meaning only 16 seedlings out of over 3,000 in the test area were missed.
99.5%. That is better than a human crew walking a transect would achieve.
It almost certainly is. Human counters in stocking surveys have inherent variability. They get tired, they miss seedlings hidden under brush, they have different counting methodologies. The AI is consistent. It processes every pixel the same way every time. And the drone can cover a 20-hectare cut block in about 30 minutes of flight time, compared to a full day of walking for a field crew. A study in Finland demonstrated a two-stage UAV flight pattern specifically designed for seedling inventory. A high-altitude flight at 60 meters for initial mapping, followed by low-altitude flights at 30 meters over areas of interest for detailed counting. The whole approach was designed to be done with consumer-grade drones costing under $2,000, making it accessible to small forestry operations.
Let us talk about the companies actually implementing this at scale. Who are the leaders?
There are several fascinating players. Morpho is a French-Brazilian company doing large-scale reforestation using drone seeding and AI monitoring. They developed a tool called Seedling ID in partnership with Google's AI teams under Google's Startups for Sustainable Development program. Seedling ID uses high-resolution drone imagery and machine learning to identify and track tree species as early as 6 months after planting. It can identify around 10 species with high accuracy, providing the species name, tree height, and crown width for each detected seedling. They are already using it across 23 reforestation projects in Latin America, spanning the Amazon, Mata Atlantica, and Cerrado biomes.
What does Morpho's full workflow look like?
It is a complete end-to-end system. Stage 1 is site analysis using drones and satellites to map topography, water resources, and vegetation cover. They also do laboratory soil analysis for compaction, moisture, and mineral composition. Stage 2 is species selection from their in-house catalog of local and endemic species, with seeds collected by local communities. Stage 3 is drone seeding, where a single drone can restore up to 50 hectares per day, dispersing up to 180 seed pods per minute. Stage 4 is the long-term monitoring, which is where the AI really shines. They capture high-resolution satellite images every 3 months and conduct on-site drone surveys every 6 months during the first 3 years. The AI models translate that imagery into actionable data: plant cover percentage, germination counts by species, growth trajectories. Their Cover Drone ID tool creates maps at 0.3 centimeters per pixel resolution, allowing them to detect vegetation changes that would be invisible to satellite imagery alone.
Who else is operating in this space?
Skylab is a German company founded in 2016 that focuses specifically on forest AI and remote sensing. They offer a seedling counter product that provides precise results for seedling density, weed cover, and vitality. They also have a forest health monitor for ongoing forest condition assessment. Their platform, Skylab Cloud, is a cloud-based service where you upload your drone or satellite data, and they process it through their AI models. They can work with normal color RGB, multispectral, hyperspectral, or LiDAR data, selecting the most efficient data source for each task. They also provide carbon project monitoring, which ties seedling survival directly to carbon credit verification.
That carbon credit connection is huge. How does AI monitoring change the carbon verification process?
This is one of the most commercially important applications. Every forest carbon credit needs spatial verification. You need to prove that the trees you planted are actually growing, that the density meets the project specifications, and that the carbon sequestration estimates are based on real measurements, not projections. Traditionally, this required expensive field verification campaigns. With AI-based satellite and drone monitoring, you can provide continuous verification data. Bondi, a reforestation organization in Madagascar, partnered with Omdana to develop a machine learning system that uses satellite and drone imagery to track and quantify the progress of their reforestation program. The AI generates the evidence package for carbon credit certification, including spatially explicit data on planting density, survival rates, and biomass accumulation. This dramatically reduces the cost of verification and makes smaller carbon projects economically viable.
Let us get into the technical details a bit more. What spectral bands and vegetation indices are most useful for monitoring young plantations?
For Sentinel-2, the key bands are the visible red, the red edge bands at 705 and 740 nanometers, and the near-infrared at 842 nanometers. The red edge bands are particularly valuable for forest monitoring because they are sensitive to chlorophyll content and vegetation stress in ways that traditional NDVI misses. Researchers have developed a new Sentinel-2-based vegetation health index that captures early stress signatures before they become visible in standard NDVI. For regeneration monitoring specifically, a time series approach works best. You track the NDVI trajectory of each planted block over months and years. A healthy regenerating block shows a characteristic recovery curve, starting low after planting and gradually increasing as the canopy develops. Blocks that deviate from the expected trajectory get flagged for investigation. The Z-NDVI approach, which standardizes NDVI values relative to historical baselines, is especially effective at detecting anomalies.
What about the challenges? Where does this technology still fall short?
Several significant challenges remain. First, the canopy cover problem. In the New Brunswick study, under very high overstory canopy cover, the accuracy of sapling density estimates from Sentinel-2 dropped significantly because the satellite cannot see through a dense canopy. LiDAR helps here because it penetrates gaps in the canopy, but it is expensive to acquire. Second, species identification from satellite imagery is still limited. Sentinel-2 at 10 meters cannot reliably distinguish between planted spruce and natural birch regeneration, which matters for stalking surveys. You need drone imagery or very high-resolution satellite data for that. Third, the first year after planting is the hardest to monitor from space. Seedlings are tiny, often less than 30 centimeters tall, and the spectral signal is dominated by soil and competing vegetation. Morpho's Seedling ID can detect seedlings at 6 months from drone imagery, but satellite-based detection really only becomes reliable in year 2 or 3. Fourth, training data requirements. You need good quality field survey data co-located with imagery acquisitions to train the models. Organizations that have been diligent about geo-referencing their stalking survey data have a huge advantage.
What about the integration of LiDAR with satellite data? You mentioned that earlier.
The New Brunswick Acadian Forest study is the definitive work on this. They compared random forest regression models using LiDAR alone, Sentinel-2 alone, and the two combined to estimate sapling density. The key finding was nuanced. LiDAR alone was the most accurate for sapling density estimation because it can detect the three-dimensional structure of understory vegetation. Sentinel-2 alone was less accurate but still useful, especially in more open conditions. Combining both improved accuracy by about 15% over Sentinel-2 alone, but did not significantly improve over LiDAR alone. The practical recommendation is, if you have access to LiDAR, use it. If you do not, Sentinel-2 can still provide useful regeneration assessments, especially in recently harvested blocks with low overstory. And they specifically recommended acquiring imagery in the fall when deciduous canopy is down, and conifer seedlings are more visible in the spectral data.
For a GIS analyst at a forest company who wants to set this up, what is the practical getting started guide?
Start with what you have. Pull Sentinel-2 time series for your management area through Google Earth Engine. It is free. Generate NDVI time series for your planted blocks going back to planting date. Even without machine learning, you can visually identify blocks with anomalous recovery trajectories by plotting the NDVI curves. That alone gives you intelligence you did not have before. Next, dig out your stalking survey data from the last 5 to 10 years. Clean it up, make sure the plot locations are accurately geo-referenced, and match them to your Sentinel-2 time series to build a training dataset. Then, train a random forest model to predict stalking class from the spectral data. Scikit-learn in Python or the random forest package in R can do this. You do not need deep learning to start. For the drone component, start small. Buy a consumer drone with a decent camera. Fly a few recently planted blocks at 40 to 60 meters altitude and experiment with object detection models. The open-source Detectron-2 library, or YOLOV-8, can be trained to detect seedlings with surprisingly little training data if your imagery is high quality.
What does the Canadian Forest Service specifically have in the works for this?
The Canadian Forest Service has been building national-scale remote sensing infrastructure through the National Terrestrial Ecosystem Monitoring System, developed in partnership with the University of British Columbia and the Canadian Space Agency. They are producing satellite-based forest inventory attributes that include quantitative measures of vegetation return after disturbances, which is directly relevant to regeneration monitoring. Their approach is nationally consistent, meaning the same methods apply from British Columbia to New Brunswick. They also have the Biospace Program, a joint project with the Canadian Space Agency, using remote sensing to monitor biodiversity and landscape changes. For silviculture specifically, the existing framework captures whether basic silviculture obligations have been fulfilled based on stocking, but the satellite-based approach promises to make this assessment continuous and quantitative rather than categorical and periodic.
The Meta and World Resources Institute tree canopy height map is relevant here too, isn't it?
Very much so. Meta and the World Resources Institute launched a global map of tree canopy height at 1-meter resolution, with all the data and AI models freely available. For silviculture monitoring, this is a potential game-changer. If you can get 1-meter resolution canopy height data globally, you can track the growth trajectory of planted trees at a level of detail that was previously only possible with LiDAR. The underlying technology uses the Dino Foundation model to connect high-resolution satellite data with field-based forest inventory measurements. For a forest company, this means you could potentially track the height growth of your plantations across your entire tenure using free, publicly available data. We are not quite there yet in terms of accuracy for small seedlings, but for plantations that are 3 to 5 years old and above, it is already useful.
Let us look ahead. Where is this technology going in the next few years?
3 major developments are coming. First, the European Space Agency is launching new satellites with higher spectral and spatial resolution. Combined with planets' daily coverage at 3 to 5 meters, we are approaching the point where satellite imagery alone can detect individual tree crowns in young plantations, eliminating the need for drone flights in many cases. Second, foundation models like Prithvi and the tools we discussed in earlier episodes are going to make it trivial to fine-tune regeneration monitoring models for any geography. A forest company in Chile will be able to adapt a model trained in Finland with minimal local training data. Third, the integration of AI monitoring with autonomous drone systems means the entire workflow from image capture to analysis to reporting could be automated. Imagine a drone that flies itself on a programmed schedule, captures imagery of your planted blocks, runs the AI analysis on board, and sends a report to your dashboard flagging any blocks that need attention. The technology for each piece exists today. Integration and operationalization is the remaining work.
This has been an incredible deep dive. The practical applications for silviculture are real, and the cost savings are enormous. For anyone in forest management, this seems like the most immediately actionable area of geospatial AI.
I completely agree. This is not theoretical or 5 years away. Companies like Morpho and Skylab are doing this operationally today. The tools are accessible, much of the satellite data is free, and the ROI is clear. If you manage planted forests, and you are not exploring AI-based regeneration monitoring, you are leaving money on the table and missing opportunities to improve your silvicultural outcomes. Start small, build your training dataset, and iterate. The technology will only get better from here.